record. Okay, perfect. Okay, so how was this week?
Once I got to it, it took me a while to get to it. I didn't really get to going through it till last night.
Okay.
So,
Did you have time to go through the Hubble's Law worksheet?
I just started it. I'm about probably 3/4 way through.
Okay, you want to go through that?
Sure.
Okay. I think that would be the most useful, like, if people are watching this recording. Okay, you want to go one by one and you can explain if you want, and I'll just like give you feedback.
Okay. In number one, everything doubles.
Exactly.
So 3 billion light years becomes 6.
Mm-hmm.
The 2 becomes 4.
Exactly.
2.5 becomes 5. The 1 becomes 2.
Okay, good. Okay. And so second question.
Second question is from A. B is going to be the furthest way because it's furthest way to start with.
Yes, okay, very true. Or in this question, I just want you simply like to see that the B will move by 3 billion light years, right? So it starts at 3 and then it's like 6, so it moved by 3. While this one will, let's say C will just move by 2 billion light years.
Mm-hmm.
Okay, very good. So then which student is correct?
Student 2 has the most complete answer.
Mm-hmm. Okay. Yes, I guess student 2 knows the math, right? So the distance is double in size, but I don't agree. They all increase by the same number of light years. And then he explains what we also kind of reasoned now. Okay, very good. How about question 4?
If they start off further away, they're going to have higher velocities initially and even higher velocities once it's doubled.
Yes, very good. So, well, initially we don't know what's the velocity, right? Because it's just like, I don't know, cut in time. So you're looking, this is the distance. But now if you're looking over that, like whatever period of time when it doubles in size, the speed of the galaxy B will be greatest because it will be 3 billion light years over that period of time. While this one, let's say C, will move just like 2 billion light years in that same amount of time.
From Hubble's law, we know that the one that's furthest away still is going to be moving the fastest away from us initially, right?
That's true. That is the Hubble's law. However, like this is the graph, right? For the Hubble's law, this figure 2, like, when I was like, your age student, just like starting, when somebody like told me, okay, this is the graph and this is what it means that the universe is expanding, that wasn't like really obvious to me, right? But when you start with this picture, I think actually this is very good idea, a very good, like, approach actually to understand that. So then you can see that farthest away something is, and then if everything doubles, then that thing that is farthest away initially will appear to move fastest away from you.
Yeah.
Okay, very good. And so now question B. I mean 5, sorry.
They all would observe the expansion of the universe the same.
So they would all observe exactly the same relationship. And the relationship was basically the further out they are, the fastest they're moving. So you can do the same thing, like, put yourself in a galaxy C, and then looking from here, you would see that the galaxies A and B would be moving faster away from you than the galaxy D, right?
Yep.
So that's basically what it means. They would all observe exactly the same. Okay, very good. Now, how about question 6?
The Hubble plot in figure 2 shows the relationship as you go further away, your velocity increases, as we've seen in the figure 1.
In figure 2, you mean this one? Figure.
As we've seen in figure 1, figure 2 shows the same relationship.
Exactly, very good. So this is exactly the relationship we are talking about, this graph, right? The further out something is, the faster it will be moving. Okay, very good. Now we are starting kind of a harder things. So how about now questions like 7, 8, 9?
Which Hubble plot shows the figures? Okay, tripling in time would mean that our slope has to be steeper. So figure 3 has a steeper slope than figure 2 above. And figure 4 has less of a slope, so that means it would be older. So figure 3 is the one which best represents problem number 7.
Yes, because the steep slope means simply that the galaxies are moving faster away from each other, right? And so
Yep.
if something is moving faster away from each other, then it will reach like larger size in the same amount of time. Okay, very good, great. And then they explain that over here, right? First, they kind of want you to see if you can use your own like intuition to figure this out, and now they explain that expansion rate basically depends on the slope. Okay, very good. How about question 8?
The expansion rate would be constant because it's a linear relationship.
Very good, exactly. So if you have this line, simply that the slope is constant, that's the basic math, and that's what you see over here. If this was like a curved line, then it wouldn't be constant. Okay, very good. Number 9.
Fastest, slowest would be figure 3, figure 2, figure 4.
Yes, very good. Okay, what's your major?
I have a bachelor's in math and a heavy minor in physics.
Oh, okay, very good. Are you taking any physics classes?
I haven't taken physics classes for a few years.
Okay, okay.
Chemistry and biology and
Okay, good. So what do you plan to do?
I don't know. When I
Okay.
figure out my life, I'll figure it out, I guess.
Okay, great. You're doing very well in astronomy. Okay, question 10 then.
If the expansion rate was faster, of course, it would reach its current size a lot faster.
Exactly. And yeah, in the class, I always tell students this is the same, like you can think just like about like driving, right? Everything starts from the same point, and then expansion simply means it moves away from each other. So the faster they're driving away from each other, the steeper the slope is, the sooner they will reach like particular size.
Yeah.
Okay, very good. How about question 11?
Which plugs to the youngest universe. The one with the steepest slope gets to the same size the quickest. The one with the least slope gets to the same size as slowest.
So which one is then the youngest? Which would mean which one would
that would be 2, figure 2?
Yes, very good.
Or figure 3, sorry.
Figure 3, right? This one would take the least amount of time to get to a particular size. Okay, very good. And then how do we fill in the blanks?
For the universe, the same size, the universe it depends on which one you choose. If you do younger, then it's the wait.
For the two universes.
Younger than younger for expansion, right?
Yes.
The line of the Hubble plot for the younger universe will be steeper. For the older universe will be flatter.
Yes, very good. Okay, great. And then how about questions 13 and 14?
Okay. 13, 0 means constant velocity. So it'd be a horizontal line going along with distance.
Okay, very good. Horizontal line like that, right? Along the distance axis, very good. And actually, like just as a side point, that's the universe that Einstein believed in, right? The one, what we call the steady state, the one that was not expanding, but it's just like kind of the galaxies were seeded in the space. So like in Einstein mind, you would just have like a flat line over here, right? Nothing is
a flat line at the distance, horizontal along the distance axis.
Yes.
Or could it be raised above it?
No, it's actually like, for which the expansion rate is 0. So nothing is expanding, right?
Okay.
So I would put it along the distance line, or you can put it somewhere here, but then mark the 0 velocity there.
Then you have an initial velocity. Yeah. Okay.
Okay, good. How about question 14?
Question 14. It starts off steep and then arcs up as you get further away to some amount.
Okay, so does that look like a figure 7 basically?
Yes, similar to that.
Okay, very good. Excellent. Okay, so now let's go through this one. And if you don't mind, just explain, because usually I know in the classroom, this is very confusing for students. Okay, so let's see with the first one. It says, draw a circle around the galaxies for which we receive light that was emitted closest to our present time.
That's close, velocity close to 0, distance close to 0. So right at the origin point.
Okay, here, right?
Right out there.
Yeah, and why is that the case? Why do you don't say here? Because usually students would say that in the class.
because because the distance away from us, of course, is close. So that means small distance. It means down on the distance axis, and then that implies that it has to be a velocity delta.
So basically, the small distance away means we are looking less into past, right? Less of a look back time. So that means like present time over here.
Yep.
Further away you look from us, the more it took for light to travel to reach us. So we are actually, exactly, we are looking into the past. Okay, so closer to the Big Bang. Very good. So I like also to in the class do like if I was to draw the time runs like this, right? This is the time going like from the closer to Big Bang, exactly, to the present.
To the current, yeah.
Very good. Okay, and then how about now draw a square around the galaxy which receive light that was the farthest from our present time. So you already said.
Right, clear up to the top, yes.
The square should be here. Okay, very good. And then?
I see to the arrow that galaxies are moving away from us with the fastest velocity to be still those galaxies clear up in the right hand.
Exactly. Exactly, because the velocity scale simply goes like from like low numbers to high numbers up over here. So the fastest velocities are these galaxies. Okay, and then the slowest would be here. So that's
there. Yes.
Okay, so how about E?
Steepest slope is initially right at the start of the ones closest to us are moving away or the rate of change of movement away from us is the quickest.
Okay, so basically the slope, like, if I approximate this to be a line, this is the slope, right? And here, basically, it's almost the flat. This is the slope. So I can see that this is the steepest slope over here, okay?
Yep.
And so this is the lowest velocities away from us because it simply means it's close to us, but the expansion rate
is accelerating quicker.
Exactly, very good. Okay, let me just like delete all of this, clear all. Okay, good. Fine. And then what do we have? F. So flattest slope, we already said over here, earlier in the time. Very good. And then F. Oh, that was F, sorry.
That was F.
Okay. Fastest expansion rate, we already said here, where the slope is steepest. And then this is the past or early universe, the flatter slope. Okay, very good. And so this would be the fastest expansion rate. This would be the slowest expansion rate. Okay, what else we have here? Okay. So now what do we say? Based on the figure 7?
It's changing with time.
It is changing with the time because it's not anymore the flat line, but it's the curved line.
So it's speeding up over time.
Yes, exactly. So mathematically speaking, at every single point over here, the slope is different, right? It's flat here, low expansion rate, and then it's speeding up as we are looking towards the...
And since we're going back in time, that means that expansion is speeding up.
Okay. Okay, so nearby galaxies, are they expanding faster than the...
Than galaxies far away.
Yes, very good. And this one you already answered. So what is happening with the expansion rate as the time goes?
We're increasing over time. We're expanding.
Very good. Yeah, and which student is correct?
It's not one. So student 2?
Yes. So the farther we look into space, the farther we are looking back in time. Since the slope of Hubble plot is flatter in the past and steeper now, that means the expansion rate has sped up over time. So student 2 is correct. Okay, great. Okay, you did great.
Good.
Okay. Good. Okay, any other questions?
Graphic on the practice, the first graphic after the 2 simulations.
Okay.
Did not want to work for me.
Wait for a second. So that would be, let me share so you can that you can tell me then which one you have in mind. So share screen, this one. Okay, so what didn't work for you in the lectures?
In the weekly participation for chapter 16.
Okay. Which one didn't work?
Okay, it's after the 2 tutorials. Hubble's law tutorial, and then I think it was the next one after that.
So Hubble's law tutorial, and then this narrated figure, visual activity.
I think that was narrated. Yeah, maybe that was one which didn't work. One of them did not. So I had to guess my way through it.
Oh, okay. So let's say if anybody's listening, if anybody else has problem, is this the one, Chad, that was not working?
No, I think I made it through this one without even looking at it, tell you the truth.
Oh, okay, good for you.
Well, I already did the tutorial. The tutorial already went through all this, so did the book. So
Okay.
I don't know.
Maybe it's the ranking task?
Or was it the expansion of the universe? It might have been the expansion of the universe one. Because there's one of them which I didn't know quite. You had to go through it and use some simulation to do. No, I got that one.
Okay.
That it was like the first one where you had a simulation off to the side which you had to play.
Okay.
And it was not refusing to work on my computer.
Okay, fine. If you don't mind, maybe after we finish, just email me which one was that, and then I'll take a look.
Yeah, I'll go back and find it.
Yeah, and if that doesn't work, I can just lower the points or add points, whatever.
Okay. I think I got most of the points on it. It just I had to guess and check.
Okay, good. Email me, please, if you don't mind, so I can then email them and tell them that it doesn't work, or I can check.
Yeah, I'm sorry I didn't. I should have wrote it down when I went through it.
Okay. Anything else?
No, I think writing prompts. How long do you want the answers for each? For the Hubble homework, how long do you want the answers? Just a small paragraph?
Yes.
Short answers for that? What about for the writing prompt? Do you want long, how short or how long?
Not too long, just to be on a point. Do you want to go through these questions?
We can if you would like to.
Sure.
Okay. The first question I really don't know much about.
Okay. Well, if you have a cluster of galaxies, okay?
Yeah.
So, and I usually mean by that not the local group, not like the Milky Way Andromeda cluster, but a cluster that can have thousands of galaxies.
But then they have more elliptical galaxies,
exactly.
Right?
Very good. Very good.
Galaxies tend to have more disk or.
Exactly. Because what's the point when you have a lot of galaxies? What will eventually happen between them?
Collisions, which will convert it into elliptical.
Exactly. Very good. Okay, the next one.
Because we could actually finally measure the distance to the Andromeda galaxy.
Because he found.
Knowing that, we knew that the universe was a much larger place than what our Milky Way contained.
Okay, very good. Because of that period luminosity, right, relationship that there is for. Okay, very good. And that's for me, we all know that, for a long time we thought the universe was geocentric, the Earth in the center, but it's also really fascinating. I think that only in the last 100 years, not even 100 years, we figured out that we are not, in the sun is not in the center of the Milky Way galaxy, and Milky Way galaxy is not the whole universe, right? Yeah, exactly. And now we know about trillions of galaxies in the universe. So we came a long way, I think, in the last 100 years.
And we know that none of those galaxies are the center of the universe because they're expanding relative to us.
Exactly. And relative to each other. So there is no central point from which everything is moving away. Everything moves away from everything else.
At least from our observable perspective.
Exactly. Very good. Number 3.
Look back time and distance galaxy. Well, anytime which we look at distant galaxies, that light takes time to get to us. That means that we're looking at the galaxy way back when that light was emitted and started.
And so basically, look back time really when you talk to astronomers that study the galaxies that are really, really far away, nobody will quote a distance because the distance is meaningless when you're talking about things that are far away. If something something sent a light and the light was traveling for 4 billion light years to get to us, it's not really at the 4 billion years to get to us. It's not at the distance of 4 billion light years away from us because during that time the universe has expanded and that galaxy has now completely different distance. distance from us. So we usually don't talk about things that are really far away. We don't talk about their physical distance, but we talk about the look back time, right? And that's the difference, because that tells us how much in the past we are looking, basically. Okay, and the number 4.
SRG A-star is the center of our galaxy. It's a massive black hole, the supermassive black hole, whichever one you would call it, in the center of our galaxy. It's what, 400 million solar masses?
4 million solar masses, yes. So what evidence suggests that it contains a massive black hole? How do we know that it's massive?
We have several stars which orbit around it, both in close proximity of it, and we can measure their period, and from that we can use Kepler's and Newton's laws to go and find the mass in the center.
Yes, great. And that study, I think, to make it even like more interesting, is done at UCLA, right? From like for the last 20 or so years, they traced those stars, nearby stars that orbit a supermassive black hole. So they constructed really precisely their orbits, and from the orbital parameters, then, as you said, using Kepler's and Newton's laws, they can figure out that there is like what's the gravity involved, and basically that there is a supermassive black hole there. Okay, very good, very good. If with the X-ray telescopes, we also have the evidence from the X-ray telescopes,
because it emits from its
accretion disk, right?
Source, right?
Yes, very good. And sometimes you even see like things like falling towards the event horizon, and then like some radio emission emitted. So there is multiple evidences that point to the same thing, that there is a massive black hole there. Okay, very good.
The only other question which I did think of was there was a question about if our radar distances were off by 10%. Within our solar system, measuring our distance from us to the sun, what would that do to parallax, and then to cyclic, and then to supernova?
Where was that question?
It was in the chapter 16 participation.
Okay, do you remember which one is that?
It was just one of the questions.
Like one of these problems or something?
Yeah, it was one of the problems.
Okay, let's see if I can see which one is that. Okay, this one is easy.
Yeah.
Okay, Safi, it's not this one.
It might have been one of the earlier problems, to be honest. Are you on mine or not?
Okay.
I don't think I've completed this far down yet.
Oh, you haven't done this? So it's something before?
No.
But is it chapter 16 or 15?
It's on chapter 16. It's probably one of the first problems that's on 16.
Okay, let's see. I started with the first one, though.
Did you start with?
I did so. With the first, problem.
Okay.
Is it maybe something else?
I don't know. I know but the problem was that I know that if you take 10%, if you have 10% error to start with, it propagates each time. So a 10% error will turn into a 20% error, will turn into a 30% error.
Okay.
Doesn't it propagate each time?
Is this the one? Imagine that the radar had never been invented. And
I know the correct answer is they all would go off by the same 10%.
Let me read this. Imagine the radar had never been invented, and we instead had to rely on less reliable methods of measuring distance in our solar system. If that method led us to underestimate the sun, the Earth by 10, how would it affect other measurements in the distance chain? So the other ones are which one? The radar. So you have the parallax. So it would definitely affect the parallax, right? Yes. Because it's the base basically of a triangle, right? So yeah. What was the correct parallax? Would also be off by 10.
Would affect all. They would all be off by the same 10%. Is what the answer which it wanted was.
This one.
Yes. Now, but I do know that every time you multiply an error, it goes and becomes larger. So each error should get slightly larger as you go along, as you go further out.
Right. Yeah,
right?
that is correct. Exactly. If
But
basic,
it wouldn't go 20%, it wouldn't go 30%,
it
40%.
should not. It should not. Because it should be like, something distance between the sun and then multiplying something else. So it's always going to be 10% off if that's involved in the other measurements. But the other one is MS fitting, main sequence fitting. And that would basically, that involves, oh, that's correct. Okay. Because then it also involves the distance measurements, right? Because that uses the inverse square law. So you're looking at the brightness and then you're trying to get the luminosity from the HR diagram, right? When you figure out basically what type of a star that is. And then that also then has to do with, that's how we determine the distance then to the stars. Yeah, so the B is the one that sounds like, correct.
Okay. I know that we're multiplying errors also.
Mm-hmm.
When you multiply that same error times itself, it becomes a little bit larger error, a little bit larger error, a little bit larger error.
Mm-hmm. Mm-hmm.
Because of error propagation. I know
Exactly.
that. Okay.
Okay.
That's all I had.
Okay, good. Then, so the next week is the last one. And so there is a dark matter worksheet, and that's going to be kind of similar like Hubble's, maybe involves like a little bit more of thinking. So I'm thinking maybe it would be also good to have it like later in the week.
Okay.
Thursday for the Zoom meeting, if that's better. But then that should be like the priority to be done, the dark matter worksheet.
Okay. Yeah, I shouldn't have any problem this week. I drove 24 hours in the last couple days, so.
Okay. And I just came from Chicago as well. I landed at 6 p.m. from Chicago, so that's okay.
Yeah. So I'm getting caught back up. I'll get there.
Okay, good. So then I'll send an announcement about the meeting next week, and then that is the last week of the course.
Yep. Okay.
Okay.
Have a great night.
You too. See you then next week.
Bye-bye.
Bye.